This is a follow-up to the previous video about a hello world example of AI game using optimization techniques in C++. Billy will first explain to you the game and the techniques we use.
The game we consider is a simplified version of NIM. The rules of the game are very simple. The game starts with a pile of n blocks. Two players take turns removing blocks from the pile. On each turn, a player may remove k blocks, where k is larger than or equal to 1 and smaller than or equal to the floor of n over 2. The player who is forced to take the last block loses. For example, suppose players A and B play with an initial pile of n equals 5 and A goes first. Since floor 5 over 2 is equal to 2, A may remove either 1 or 2 blocks. Suppose A removes 2 blocks, leaving n equals 3. Now it's B's turn. Since floor 3 divided by 2 equals 1, B can only remove 1 block. After B's move, n equals 2. A then removes 1 block, leaving n equals 1. B must take the last block and therefore loses. Thus, player A wins. The NIM game can be modeled using the Minimax tree introduced in the previous video, where we explained in detail how Minimax works and how it can be implemented. The figure below illustrates a Minimax game tree for NIM with an initial pile of n equals 6. Circles represent internal nodes, decision points. Squares represent leaf nodes where evaluation occurs. In this game, one of the two players must win. There are no draws. For simplicity, we assign the following scores. +1 if the first player wins. -1 if the first player loses. Let's call the first player A, the second player B. When the game starts, A has 3 choices. It can remove 1 block, or 2 blocks or 3 blocks. If it removes 1 block, remaining n equals 5. B has 2 choices, removing 1 or 2 blocks. If it removes 2 blocks, remaining n equals 3. A can only remove 1 block, remaining n equals 2. B removes 1 block, n equals 1. A has to take the last block and thus loses, so the score is -1. Similarly, at here B takes the last block, thus A wins, so the score is 1. Here and here A loses and thus the scores are -1. Here and here A wins and thus the scores are 1. As discussed in the previous video, A always chooses a path that maximizes the score while B always chooses a path that minimizes the score. We can work from the leaves up to fill out the scores of the internal nodes. For example, consider this left branch. The maximum of 1 is 1. The minimum of 1 is 1. The minimum of -1 is -1. The maximum of 1 and equals 1 is -1. The minimum of 1 and -1 is -1. The maximum of -1, -1 and 1 is 1. In the game, A chooses this path that maximizes the score.
This program demonstrates the implementation of the NIM game using the Minimax algorithm. The Minimax class used here is essentially the same as the one we introduced in the tic-tac-toe implementation from the previous video, with some minor modifications. Here we define the data type player with 2 members, max and min, and this is the node with a score and move. And this is the Minimax class for the NIM game. We call it Minimax NIM. Okay. It has 2 private members, player AI, and op means opponent, the opponent of AI. And others are public members, n here is the number of blocks in the pile, and turn tells which turn is to play. And so this is a constructor of the class with the players passing in AI and op, and also the initial number of blocks. Check winner is to check who is winning. So it returns 1 if AI wins, and returns 2 if op wins. So if the turn is op and n equals 1, so AI wins. Otherwise, op wins. If it is not determined, it returns -1. And the loss function, Boolean, will tell whether the player has lost. So if the turn is the player and n is 1, then that's true. That means it has lost. Otherwise, it's false. Remove k is to remove k blocks from the pile. So n becomes n minus k. And evaluation is to evaluate the score at a leave. So it depends on the state. If state equals 1, it returns 1. Otherwise, it returns -1. So the state will tell you who is winning, as you will see later. Now here's the core part of the Minimax algorithm. So this variable max tells whether it is the maximizer's turn or the minimizer's turn. If it is true, then it's maximizer. Otherwise, it's minimizer. And the depth is the level of the node being evaluated. It starts from the root with depth 0, and then 1, 2, and so on. So it defines the state with a value 64. And so if the opponent lost, the state is set to 1. And if the AI is lost, then the state is set to -1. And then in the evaluation, we get these scores. Evaluation. And then create a node with the score and return the node. So that's the exit case of this Minimax function. Otherwise, we have to call this function recursively. So first we remember the turn. If max is true, so we start with a small value of score, we set to -64, and m is the maximum number of blocks that is allowed to be removed. It is n divided by 2. So this is integer division, so it truncates, which is the same as the for function. So we have to try all the values from 1 to m. And so when we remove I blocks, then the remaining number of blocks will be n equals n minus I. And the next turn would be the other player. So if the current player is AI, then the turn will becomes op. Otherwise, as the next turn is AI. And then we do this recursively. So I call the Minimax function with increasing the depth, depth +1. The next turn will be false. So that means we start with here, next we call it becomes mean, and mean we'll continue to call, okay, it becomes max, okay, and then if we just leave, okay, then it exit and returns. Okay. And after this recursive call, we have to restore the n, so n equals n plus I, and we store also the turn, and then we need to find out the maximum score and the corresponding move. Okay. So there's the code for the maximizer. Similarly, we have the code for the minimizer is just reversed. Okay, start with a large score and take the minimum. Okay. So this code is basically the same as the one that we discussed in the previous video. So this is the main that give a test, okay, to test the code. Okay, now let's copy this code and try. So we copy this file and paste it into Minimax nim.cpp, and save it. Let's compile it. So we get the executable Minimax nim. Now let's execute it. Let's try 7. So AI takes 1. The blocks remain is 6. As you can see from this diagram, if we start from 6, if we remove one block, then we are going to lose. Okay, because this is -1. If we remove 2, we will lose also. If we remove 3 blocks, then we are going to win because there's a 1. Okay. Now let's try removing 1 first. Okay. So the box remain 5. AI takes 2. So box remain 3. So we are allowed to take the only 1. So 1. So box remain 2. So AI takes 1. There's 1 block remaining. So AI wins. That means we lost. Okay. Now let's try the other path. Okay. Again, we start with 6. So if we take 3, then we are going to win. And the other one will take 1. Okay, then we win. So we take 3. Okay. So the AI takes 1, box remains 2. So our move is 1. Okay, so we win. Okay. Then let's try a larger number, say 20. Okay. And say randomly we say 7. Okay. And then 3. Okay. And then 1. So AI wins. Okay. Because AI optimizes the moves. And suppose we try an even larger number, 50. Okay. And you can see that the program never returns. It just hangs there. Now, Buildy will explain to you what is happening.
The program does not return in reasonable time when n becomes large because the execution takes too long. The running time Tn of the Minimax routine with input n can be expressed as Tn equals Tn minus 1 plus Tn minus 2 plus Tn minus n over 2. Solving this recurrence shows that Tn grows exponentially. That is, Tn is essentially 2 to the n. This exponential growth occurs because the algorithm repeatedly solves the same subproblems many times. A more efficient approach is to use dynamic programming, DP. The key idea is to store intermediate results in a table, so that previously computed values can be reused instead of recalculated. For example, consider n equals 6. Using plain Minimax, the algorithm will recompute values for smaller states such as n equals 3, n equals 2, and n equals 1 many times along different branches. With dynamic programming, we compute each value only once and store it. In the above example, we have the base case, n equals 1, which is a losing position. When we compute n equals 2, we check possible moves, k equals 1, leaving n equals 1, which is a losing position, so n equals 2 is a winning position. When we compute n equals 3, we have possible moves k equals 1, leaving n equals 2, which is a winning position. Since the opponent faces a winning state, n equals 3 is losing. We continue the computation until n equals 6, using stored results instead of recomputing. This way, each subproblem is solved only once, reducing the total runtime from exponential to linear in n. This table shows the scores of the player starting with different values of n up to 7. When n equals 1, the player is losing, so its score is -1. When n equals 2, the player removes one block, leaving n equals 1 with score -1, meaning its opponent is losing, so it is winning and has score 1. When n equals 3, the player can only remove one block, leaving n equals 2 with score 1, meaning its opponent is winning, so it is losing and has score -1. When n equals 4, the player can remove one or two blocks. It could remove one block, leaving n equals 3 with score -1. So it has a path to win and its score is 1. When n equals 5, the player can remove one or two blocks. It could remove two blocks, leaving n equals 3 with score -1. So it has a path to win and its score is 1. When n equals 6, the player can remove 1, 2 or 3 blocks. It could remove 3 blocks, leaving n equals 3 with score -1. So it has a path to win and its score is 1. When n equals 7, the player can remove 1, 2 or 3 blocks, leaving n to be 6, 5, or 4. In each case, the score is 1, meaning that its opponent always wins, so there's no path for the current player to win. So the score is -1.
This program implements the idea. The function getScore returns the score of n blocks. It also saves the score in the array S. It is a recursive call and the code is straightforward. So if n equals 1, then Sn equals -1, okay, as shown here. If it is not equal to 0, then it returns Sn. Okay. Otherwise, if the entry is not filled, at 7, at the beginning the entry would be 0. Then it will scan through all the possible cases. And if the getScore next n is equals -1, then that means we found a winning path, okay, or a path that the opponent loses. Okay, so our Sn equals 1. Like here, 4 minus 1, you get 3. This is -1, so when n equals 4, the entry should be 1. Okay, and if we scan through all the possible moves, and if we could not find any entry with -1, then the entry at that n should be -1. Okay, like this case, when we consider all this, okay, -1, -2, -3, all these values are 1, then this entry need to be a -1. So Sn equals -1. Okay? So we return this Sn. Okay? So get score, okay, give us the score of n blocks. And best move basically is to choose a winning move if the move exists. Otherwise, we pick a random legal move. Okay, so suppose the current value or the current number of blocks is n. Okay, again the score here is basically the S here. It stores the score. Okay, so m equals n over 2. And we ensure that it is at least 1. And we have to scan through all the possible legal moves from 1 to n over 2. And we try all the scores. Remember, the get score returns the score of the entry at of the table. Okay. So if the get score, if we make a move and score is -1, okay, so that means the opponent loses. So we choose this move so that the other player loses because this is -1. Okay. If we have scanned through all this and could not find a winning move, then we just randomly return a legal move. Okay. So it's very simple, very straightforward. Now here's a routine that tests these routines. Okay. So we just need to use the best move. Okay. The best move we call get score. Okay. So this is the main. So at the beginning, the score, this array is, the entries are all 0, okay? And then we start with a certain value of n between 2 to 99. Okay? And we let AI moves first, okay? Starting with the value that we entered. Okay? And so AI uses the algorithm that we discussed, best move, to find the best move. And then so we take away that number of blocks. And now, after we have taken away the number of blocks, if n is equal to 1, okay, the next turn would be you, okay, then you lost. Okay. Otherwise, we continue to play. Okay, after AI, then it's your turn. Okay, again, we find the value of n divided by 2, and we have to enter a value between 1 and n over 2. And so we take away the number of entries, number of blocks that we enter, and then we go back to AI so until we get a winner. Now let's copy and compile this program. Now let's copy this program. Copy. And let's compile it. So we save this as name dp.cpp. Now let's compile this. G++ -c name dp.cpp. So it compiles, and we get the object file lim dp.o. Now let's also copy the testing routine. So we call this test lim dp dot cpp. And we paste this, save it, okay. And now let's compile this. So compiles also, we get this objects file. Now we can link them together. Oh, sorry, I forgot the other file. Lim, yes, okay. So link them together, and we get this test lim dp. So now let's execute this. So suppose we start with the simple case 7, and so AI takes 1, so 6 remains, and suppose we move 3, then AI takes 1, and we can enter 1. So AI loss, we won. So if we did the right thing, suppose we start with 7 again, and if we don't do it properly, we say 1. Okay. So now 2 remain, and we enter 1. So AI wins this time, and we lost because we didn't pick the right move. Okay. Now let's try a large number. Okay. 50. Okay. So the AI takes 19. Suppose make simple, we make 15. Okay. And AI takes 1. So suppose we make 7, and then AI takes 1. We can pick 3, okay. And then 1, and then again we lost. But you can see that this time the program runs very fast. It doesn't hang up. Okay. So that's because we have used dynamic programming, and that takes only linear time. Finally, we present a simple GUI implementation of the testing routine. It is minimal. You can certainly improve it. Here's a quick walkthrough of the routine. Nmax is the maximum number of blocks allowed. So we define it to be 99. Best move is the function we discussed earlier. It computes and returns a winning move using the dynamic programming technique. The variable window here represents the handle to the screen window. N blocks is the current number of blocks in the pile. Take n is the number of blocks removed. State defines the state of the game. It could be 0, 1, 2, or 3. And digits array will hold the digits the user enters. N digits tells how many digits the user has entered. The array score will store the scores of the AIN. And at the beginning, the entries are initialized to 0. Game over tells us whether the game has finished. Now, this is the graphics routine. This is the main, the usual graphics initialization. We use a screen window 600 times 600. and it starts with init, calling the init routine. Display is the display callback function. Keyboard is the keyboard callback function. Now this is init, where the program starts. This defines the lighting and material colors for objects. So this is just to make the objects look more fancier. It is not necessary. Okay, so the program works fine if you remove all this. So the world coordinate is defined by GL ortho. The x, y, z are divided to vary between -10 and 10. Okay, all of them are the same. The function here, the function message here is to display the message pointed by S, or the string pointed by S. It uses this function cut bitmap character to display character by character. The function reset digits, it reset n digits to 0 and all digits to be 0. Display is the display callback function. So divide an array as that holds characters. And if n box is within 1 and n max, then we try to display the objects. We say each row has 10 blocks. A block is just a sphere. And we calculate the number of rows, n rows, using this formula, n blocks divided by 10.0. So this becomes a double, and then we take the ceiling function. So that's the number of rows we need. Okay. So each row has 10 blocks. Okay. So we display all the objects, all the blocks. And we start with state equals 0, the initial state of the game. Okay. And so as will point to this state, okay, I'm sorry, this string, enter initial blocks 2 to 99, and then display the message as. Okay. So this is a local variable as. Okay. So there's a global one as here. Okay. So the next, this as refers to this as. I have used a different relation. And so this as will contain this message with a number of blocks and also the n blocks. Okay. So all this will be saved in this array s. Okay. And then message s will display the message. Okay. And you also display this message. Press P to play AI moves first. Okay. Now if the state is true, that means AI's move. So display the message. You took means the user. Okay. Took that number of blocks. Okay. It displays message, and then move the cursor and display the other message with mean number of blocks and blocks. And if n blocks still larger than 1, then the display the message press A for AI move. Okay, next turn is AI. And coming turn maybe. And then after that, it resets the digits. Otherwise, if n box equals 1, that means AI has lost. Okay. And you have won. Okay. because AI takes the last block. So we have to press R to restart. Game over is true. And if state is free, then it's user's move. So displays this message, AI took that many number of blocks, and continue to display this message, many number of blocks, and if n blocks is larger than 1, it will display this message, you move 1 to n blocks over 2, and otherwise if it is 1, that means AI has 1. You have to press R to restart. Game over is true. So the function play is the beginning of the play. So AI calls this best move to calculate the number of blocks it has to take n. The blocks it has to remove. So the new number of blocks will be the original blocks minus take n. And the state will change to free. Next is your turn. If it says the digits and call display. Reset is to reset the game or to restart the game. The digit value calculates the value stored by the digits in the array digits. And this is the keyboard copy function. If we press escape, then it exits. If key goes out, that means we start the game, we reset. If the game is over and we haven't pressed R, then we do not do anything. Otherwise, if we enter 0 to 9, that means it's a digit. So we save the digits in this array digits. But only when state is at the beginning or the user's turn. And if the key is P, that means it's start to play. So calls this function play. If it is a return, and if it is a beginning, state equals 0, then you calculate n blocks from digits value, and then then call this. If we have enter enough blocks, and then set the state to 1. And if the state is free, that means it is the user's turn. Then we calculate n from the function digits value, which calculates the value saved in digits. And if within the legal range, then we set the digits and call the display function. And also we calculate new blocks, and we set last digit to be the key, that means return. And call the display, and we set the digits and set the state to 2. The next turn is AI. So we can call AI by pressing A, the key A, and which will call best move to calculate to return the number of blocks removed. And then we calculate new blocks, and set the state to free. So this is a simple GUI testing routine. Now let's compile and run it and try it. Now let's copy this and place it into test.img.cpp and save it. And so we just created this file and test.img.cpp, and now let's compile it. -c test g.cpp. So it compiles and creates this object file. Now let's create an executable. G. We need to link with the NIM dynamic programming routine, which is in NIM dp.o. We also need to link with the graphics libraries. Okay, so it creates this executable. So now let's execute. So this is the executable, the graphics screen, and it displays this message and the initial box. Suppose we try 7, okay. And so the 7 squares are displayed, and it displays this message: remaining number box 7. Press P to play. See, AI took 1, so remaining number box is 6. We can move 1 to 3. So suppose we enter 3. So AI's turn. AI took 1, so we took 1. Okay, so we have 1 because 1 block left. Okay, now suppose we do R to restart. Okay, suppose we try 7 and P to play. AI took 1 to become 6. Okay, so we take 1. Okay. AI took 2. Okay, and we take 1. Okay, AI took 1. Okay, so in this case, AI has 1. So suppose we press R to restart. Let's get a bigger number. 89. Okay, so we have 89 blocks. Okay, again P to play. AI took 26. Okay, so we have 63 blocks remain. Suppose we try 5. Okay, so it took 5. Remaining number of blocks is 58. So AI took 27, and 31 remains. Suppose we do 15. Okay, so 16 remains, and AI took 1. Okay, so 15 remains. So we take 7. Okay, and so 8 remain. So we take AI took 1. So remaining 7. So we take 3. Okay, 4 remain. So AI take 1. So 3 remain. So we can only take 1. Okay, and AI took 1. So the 1 block remains. So AI has 1. Okay, so so this is the NIM game with a GUI. So you can try this out yourself. Okay, so this rounds up our discussion. Thank you for watching, and I will see you in the next video.